excited to talk to this group. I love what is happening at House Accelerator, and really excited to be able to bring this piece to what everybody's trying to do, which is figure out buildings and climate and what we do and how we go forward, and keep building amazing buildings for people who need them, and not wrecking the planet as we do that, and maybe even helping rescue it a little bit. So this presentation, I warned people who came on earlier, you're getting a bit of a Frankenstein presentation in that I've patched pieces of different presentations together. I feel like this group has a very specific, already established kind of knowledge base and some interests that are unique. So all the information is here. You'll just see the kind of format change maybe sometimes between slides, but hopefully everything is here in a logical order that you're able to follow, and looking forward to a discussion at the end too. So there's one of the bases for this presentation is this report that I just helped author with Builders for Climate Action and Natural Resources Canada, which is the branch of the Canadian federal government that's responsible for home energy efficiency and all the programs that the federal government offers there. And we did this study, achieving real net zero emission homes, and it was the first time that a national government has really, taken a dive into material emissions and trying to see what they mean for the country. And it's the beginning steps of trying to figure out how this might fit into the regulatory world. So I was really excited to be part of it. But you'll see partway through this, we also segue into a bit of a presentation. We've been helping the cities of Nelson and Castlegar, BC, also study this for their region. And they're actually going to be instituting some incentive programs. And so those two bits of work are kind of coming together in this presentation. So very brief background, because I think everybody knows the story by now, but all of us have been working super hard at figuring out how to eliminate or greatly reduce at least the operational emissions that come from buildings. Such an incredible focus over the last 20 years of, if we really think back, when I built my first house, my building inspector laughed at me for wanting to put more than R12 in my walls. He just thought that was the most ridiculous thing he'd ever heard. Why would anybody do that willingly? And so it's a long, we've come a long way from then till now. And, we've all done really great work to really address that side of the emissions puzzle. But what I've been looking at recently, and honestly, my own dive into this came from about 10 years ago. I wanted to know what the carbon footprint of the building that we were working on at the Endeavour Centre that year might be, out of kind of just interest, hey, what does this look like? And that started me down a sort of 10-year rabbit hole of trying to figure that out, mostly because when I first started, I couldn't figure it out because nobody seemed to know. And then my interest kind of happened at the time that a lot of people got interested. And so a really interesting kind of body of knowledge has grown in that past decade. But the specific thing that I want to talk about is sort of the material emissions, this red highlighted bit in a life cycle of a building and its materials. And the reason that I want to focus there is that product phase, or what people often call cradle to gate, is where the majority of the emissions from all the materials that we use in buildings happen to occur. Depends on the material, but somewhere between sort of 70 to 85% of the emissions that are going to happen over the entire life cycle of a product. So from its initial raw material harvesting to when it finally is taken out of the building and incinerated or landfilled or whatever happens to it at the end of its life, almost everything happens up front here. And so when we're thinking about addressing the climate, today's emissions matter a lot, and here's where most of them lie, and this is where we can dive in and really address these. The other phases, in particular, transportation to the construction site and construction site emissions, tend to be sort of between 5–10% of the total life cycle. So not as big as most people think, but not insubstantial either. But it's hard to address that broadly, because where you are, where materials are coming from, how you're getting to the site, what kind of energy you're using on the site, all of those things are very particular and unique. Whereas the material emissions, most of these things are built in factories, and it's very easy to assess what's going on in that factory. And so we know that the emissions we're sort of recording and understanding here are quite rigorous and understandable. And so we get the data that sort of driving these studies from these documents called environmental product declarations, or EPDs. And that's an internationally standardized way of reporting on a bunch of different environmental impacts from, in this case, building materials, but the methodology is actually used for all kinds of products. So each product has a category that it falls into. So you don't necessarily use the same rules for, say, framing lumber as you do for flooring. So within each product category, there's a set of rules. But basically, an EPD makes sure that everybody's counting the same kinds of things in the same way according to the same methodology. So we get a pretty comparable look between products in the same category. And so I take the global warming potential that they report in an EPD and figure out what that means for the amount of material in a particular building. And first, for my own purposes, I started to build out a spreadsheet of all of these EPDs, and wanting to model my own buildings and some research buildings I was doing. I kind of built a sort of half-assed spreadsheet that gave me the answer, but that if anybody else looked at it, they wouldn't have known what was going on. But that has been refined over time. We built a version of it for Natural Resources Canada, which they call the MCE squared tool. We also have a version of it called Beam. Both of them are going to be out in public before the end of this year. So excited to kind of have that tool get out into the public. And you probably can't see this on the screen, but essentially, each tab on the spreadsheet is a different part of the building. This is a snapshot from the exterior walls, where we've told the software how much wall area we have. We've given it an R value. And what I really like about how we built the tool out is that right away you see a comparison for the building you're working on of the carbon footprint of all the different materials. So I can look, see, oh, fiberglass would give me this in this building, blown in fiberglass that, mineral wool this, cellulose that. So it's this really great sort of tool where you get to compare the actual results for your building right away. So you can sort of decide on making material decisions and material swaps here by seeing the carbon footprint in kind of real time. So that tool is behind this NRCan study that we just did. And the study looked at, it's not based on real homes, it's based on archetypes. So NRCan has a bungalow, a two-story, and a row house that they have plans for, that they kind of use as like the typical kind of single-family homes in the country. They gave us HOT 2000 energy models for these archetypes at tiers 3, 4, and 5 of the National Building Code, 5 being sort of the most energy efficient. It's kind of like the net zero ready version of the code. And they gave us models for 5 cities across the country: Vancouver, Prince Albert, Saskatchewan, Toronto, Quebec City, and Halifax, Nova Scotia. And then we built up 4 material scenarios for each of those models. One where we kind of picked the highest carbon option in every material category. One where we picked pretty typical selections from the mid-range of the options that are available. One that we picked what's the best material, in other words, has the lowest carbon footprint, but it is widely available and code compliant across the country. And then a final model where we just picked the best option, whether it was, you know, a typical material or code approved or not, so that we could kind of, we're sort of bookending the study with a worst case and a best case scenario, and then showing a bit of what is possible in the middle. And so this part, you're all gonna get how this part works. So I'm looking at the 2-story house from Toronto here, but things mapped out pretty similarly across all of them. So tier 3 is kind of our building code norm right now. So it's kind of like a code compliant home built today, heated and the hot water done by gas. And that building from the HOT 2000 model has about 3.5 tons of emissions per year, or I just extended that over 20 years, so 70 tons over 20 years. And that's probably about what you would all expect from something in this climate. If we bump that house up to tier 4 and it's still on gas, it's great. We dropped, you know, 20 tons of emissions over those 20 years. It's down to 2.7 per year. So, you know, clearly moving buildings along the energy tiers does what you would expect it to do. The tier 3 model, if we change it to all electric, so an air source heat pump was doing the home heating and an electric resistance heater for the hot water tank. Even at tier 3, you know, the operational emissions have dropped to under a ton per year, 14 tons for the 20 years. So, you know, obviously you can see there's a big difference between using a fossil fuel and using relatively clean electricity here in Ontario. If we bump that house, that electric house along to tier 5, we've got it down to under 0.5 ton per year, just under 9 tons for the 20 years. So all of that is not news to you. You all know that that's kind of how things go. What we're trying to provide them in this study is what is this end number after 20 years if we add the materials to it, right? Because that's this operational side isn't the only carbon footprint that building is going to have. Its materials also have ones, and we don't know that answer until we know this answer. So in the study, this is what we found. If we pick the worst materials in their category, and these are not uncommon materials, this includes things like brick cladding, it includes things like XPS insulation under the slab and around the basement, you know, spray foam insulation in the walls, you know, not unusual materials. It's this model's maybe unusual in that we put them all in one building, but you can see what happens. The carbon footprint of just the materials absolutely dwarfs the operational emissions. So, you know, the vast majority of the emissions lie here. The material emissions for this one are equivalent to 315 years of operating emissions. So, you know, if we're going to make a difference in this building, we're going to make the difference in the materials and not anymore in the operations side. Here, you'll notice that the scale has changed a bit. I had to adjust it to fit that last model in, but our more moderate materials example is 31 tons of material emissions, taking the building to 40 tons over the 20 years. And so this is, you know, this is a much lower material emission than the other one by a substantial amount, but it's still equivalent to over 70 years of operating emissions. So again, you know, even when we get into a more sort of moderate material palette, the materials are still the dominant part of the emissions profile, well past when we have to care about things for the climate. You know, 70 years is not the time when we want to start seeing paybacks on carbon footprint. So the moderate version still leaves a lot to be desired in terms of meeting climate goals. So the third model starts to look different and quite positive. This is the first model in the study that has a net carbon storage. And this was achieved pretty simply. The main things that we changed in this model were the cavity and the roof insulation were cellulose. The exterior continuous insulation was wood fiberboard, and the concrete was the best mix that we could specify for the Toronto region for this project. Pretty much that's the deal that pushes this model from having a pretty substantial carbon footprint to being a net carbon storer. And so you can see what happens if we start the building in a position of net carbon storage with a minus number. It operates for 20 years and it's still a net storer of carbon. And so I think that was the reason we titled the report achieving real net zero carbon buildings. It's because it's only a net zero carbon building if, when you add both of these things up together, the materials and the operation, it's at zero. So if we can get there, then that's where we need to be. And this is a pretty achievable model of a residential building to be able to get there. So that's going to extend out for 45 years. So this building won't have a net carbon footprint for the next 45 years, which is pretty much what we need to do. And it's pretty great to see that it is doable. Again, this model had all materials that you can go get your hands on and use pretty easily today. And then this is sort of the more ambitious model. This is using materials that maybe aren't so common. We know that they're doable because that's what I do in my day job, is make buildings like this. But so this has things like straw bale walls instead of cellulose walls. It has pressure treated wood foundation. It has things like linoleum and cork flooring in it. We sort of threw as much carbon storing material as we could at this building. And you can see what happens here is, the amount of carbon storage is actually really substantial. A building like this actually starts to be a noticeable kind of reverser of climate change and not just a zero. And so this building is going to stay net carbon storing for almost 200 years. So well past my life, my daughter's life, and whatever children she has, their life, and maybe beyond that too. So, I think if we want to be building in a way that we can really look to future generations and say, yep, we did what we could to help you have a climate that you can live with. This is where we need to be aiming our practice. So this is just those models, put together so you can kind of see the extent. Essentially we built the exact same home. It's got the same number of rooms, the same level of energy efficiency, the same number of doors and windows, functionally and operationally the same building, but its carbon footprint is, can fit anywhere in this really, really wide range. And so, I think there's a way to sort of look at this literally as a series of steps. Like if I'm here, then I need to get here and then here and then here and then here and then here. We don't have to just all get to the green right away. There's a way to sort of progress ourselves there that, each one of these steps is really substantial. Like this blue model is less than half the carbon footprint of the red, and the yellow is more than less than half of the green, et cetera. These are big steps. We could break them up into smaller steps as well. So I think, figuring out where you are on that progression and then figuring out, just how to get yourself to the next step first, and then the next step is a pretty good way to look at that. So I'm going to switch up a little bit and just talk about that carbon storage in buildings, because that sometimes it took me a while to wrap my head around that, and I know that happens a lot for people kind of hearing this for the first time. So the way all of the materials that in this study that had carbon storage are plant-based materials. There also can be carbon storage in minerals, but none of that technology is really at hand right now. Hopefully it will become soon. Things like concrete aggregate gravel made from CO2 that's pulled out of the smokestacks of cement factories. Things like that are happening now and starting to be scaled up. But right now, if we want to put captured carbon dioxide in buildings, it's going to be plant-based. So plants absorb CO2 as they grow. That's what they do. the C stays in the plant, the carbon, becomes part of the body of the plant, and the oxygen comes back out for us to breathe, which is a really great byproduct. And literally billions and billions of tons of carbon come out of the atmosphere every year this way. Just grain straw alone is 4 billion tons of captured carbon dioxide annually. That's the emissions of India, the third or fourth biggest emitter on the planet, is completely taken out of the atmosphere just by grain straw every year. But then we burn that grain straw, or we let it rot, or in some way that carbon goes back to the atmosphere and we lose it again. So the CO2 is sort of pulled down by the plants, and we kind of interrupt it by putting it in a building for some chunk of time, hopefully a decent length of time, like 60 to 200 years. And maybe then it will come out, but maybe then we'll have the climate under control. We won't be burning fossil fuels like crazy, or we'll be smart about carbon and people will do appropriate things with it when it does come out. But the idea is we're sort of interrupting that carbon flow. We're taking carbon that would have gone back to the atmosphere and sticking it in buildings for a long time so that it doesn't end up back there. And you may be wondering, that was a weird building choice, Chris Magwood. Why did you put a picture of that building here to talk about carbon storage? And I picked that one especially because it's a very large straw bale building. It's a 7-story apartment building in France, mass timber frame, prefab straw bale wall panel enclosure around the outside, probably the biggest carbon storing building on the planet. Pretty cool. We can do this right now today. This thing has a monstrous amount of carbon storage in it. And it's things like this that we're going to have to do if we really want to drive towards that sort of best case green building model. Some places that we've done that store carbon, there's a little straw bale residence. There's a hempcrete and hemp bat insulation institutional building at Trent University. There's a very large straw bale school also in France. So, we're not pipe dreaming here that this is possible. And I'm sort of using some straw examples here because that's the world I'm from, but people are doing this with bamboo, people are doing it with rice hulls, people are doing it with agricultural residues of all kinds. So these are the kinds of buildings that sort of would exemplify that green typology of net carbon storage. Because you're a technical bunch, I thought I would sort of get into the technicalities of carbon storage. This has been an interesting ride for me. I'm not a climate scientist. I'm not really a scientist of any kind. I'm a builder. So wrapping my head, I could get that, okay, carbon comes from the atmosphere, goes in the plant, stays in the building. Okay, great. But what does that actually mean for the climate? Luckily, climate scientists have thought about this and they know this and they figured this out. So what this is showing is the yellow part of this graph is starting with 1 ton of carbon emissions. So if today one of us emitted a ton of carbon, we drove our car for a few miles, poof, there's a ton of CO2 in the atmosphere. That stays in the atmosphere. It decays slowly over time. This ends at 100 years. It continues to have an effect on the climate beyond 100 years. But over 100 years, that pulse of carbon dioxide is said to do 46 ton years of damage to the climate. I don't actually know what a ton year of damage to the climate looks like, but that's sort of how it's mathematically created. So on the flip side, down here is a ton of carbon that we store. So in our building, in the cellulose insulation of your building, you put a ton of carbon. If that carbon stays in that building for 46 years, it has done the opposite of 46 ton years of damage. It's relieved the atmosphere of 46 ton years of damage. So in other words, when the green square has the same area as the yellow area, then we've offset, fully offset a ton of carbon. So, anything that we're going to put in a building that's going to last 40 to 50 years. So things like the insulation, things like the framing, things, the sort of main parts of the building that we're not going to change out. Then that's how we can sort of there's sort of a climate science justification for that being a meaningful amount of carbon storage. So what that means, everybody's always like, yeah, but when the carbon comes out of the building, doesn't it just go back to the atmosphere? Yes, it does. But in the 50 years that it's been in the building, it has done the work of taking a ton of carbon out of the atmosphere. So at that point, it's basically like it's a new emission. And obviously, we don't want, to burden future generations with lots of new emissions. But at a time right now when we're still burning fossil fuels uncontrollably, like giving ourselves this 50, 80, whatever it is, 100-year window of removing carbon from the atmosphere is, one of the few options that we have to kind of stop the runaway freight train. If we figure out how to stop that runaway freight train, we'll probably have figured out better things to do with carbon when they come out of buildings than burning it. But this is sort of, when I talk about carbon storage in buildings, that's what I mean. The stuff that's going to hang out in a building for 46 seems to be the magic number, but you can call it 40 or 50 or somewhere in that range years. And then we can also then use ton-year accounting to sort of weight the value of that carbon storage if it's there for less or more time than 40 years. So, if I put 100 tons in a building and it's only there for 1 year, then its offset value is 1/46 of its weight in carbon. If it's there for 20 years, it's almost half the amount. If it's there for the 46 years, my 100 tons in the building literally has offset 100 tons. If it's there for longer, it's actually offset more than 100 tons. It's done, more work because it's been out of the atmosphere longer. So, built into the sort of the tool that we built is that logic. If a product has a 30-year lifespan, then I'm using the 30-year storage value. If it's got a 50-year, I'm using the 50-year. So we can sort of fine tune the meaning of that carbon storage using that ton-year accounting. So I'm working right now with my colleagues on a study for the Toronto region. With Passive Buildings Canada and sponsored by or funded by the Atmospheric Fund, we're actually doing case studies of 100 recently built homes in the Toronto region. It's the first time that somebody's like benchmarked that many homes. And I just wanted to give you a sense, we're not quite done yet, but here on the left are the results from that Enercan study. So our worst case model was just under 140 tons for a 2-story building in Toronto. Our mid-range was 30, and our sort of best available materials was -20. When we actually are doing as-built homes, here's what we found. 88 tons is the worst for a 2-story home. So the worst isn't as bad as our worst case scenario, but the very best home in that whole study, or 2-story home anyway, is 50 tons, which is a whole lot worse than our sort of mid-range estimate over here. So, as we look at real buildings, we're finding that they're all kind of landing in between the red and the blue sort of model in sort of real life. And so, it's not the absolute worst case scenario, but it's far, far, far from the best case scenario. And we'll have that study out first thing in the new year. So I'll make sure that I send it everybody's way so that it gets seen. We also just finished for the cities of Nelson and Castlegar in BC. We did 35 homes there. So again, these are actual as-built examples. And there we found that the average house was 26 tons, and again, bracketed quite widely by 63 as the highest result and 5.9 as the best result. So, the average, looks good compared to the other study, but, again, like there's this wide range that they fall in. And so, super important to know that, like, in the same region within the same couple of years, people buying materials from the same store can turn out a 63-ton house or a 6-ton house, and it had nothing to do with its level of energy efficiency, or it's really comes down to material selection. And the average operational emissions from those homes were, 1.25 tons per house. So again, we sort of see a wide bracket under, well under a ton. At 0.14 was the best result, and almost 5 was the worst result. So same kind of thing, like the possible range is really wide. But if we take the average, again, we see that thing that keeps happening of it takes at least 20 years of operations if we use the average from this study before operations have caught up to materials. And from that Nelson study, this is what the sort of material categories broke down. So when we amalgamated all the results and all the materials out of that study of 35 buildings, concrete was responsible for the biggest chunk of emissions. So across the whole study, just over 34% of all the emissions were concrete. Insulation came next at 18.8%, cladding at 13.2%, windows and interior surfaces being flooring, wallboard, and ceilings are pretty similar at around 10. Framing is also around 10. Roofing pretty small at 2. And structural elements like posts and beams and things like that, pretty insignificant. And down here at the bottom is the cellulose was the only carbon storing insulation in that study, but there was in total 41 tons of CO2 stored in the cellulose across the study. So that's kind of what it broke down in Nelson, and it's pretty similar to how it looks like it's breaking down in Toronto and likely, pretty much across North America. The one that changes a lot can be cladding. Places that use a lot of brick, that tends to be higher. Places that use sort of more wood and vinyl tends to be lower, but this kind of breakdown is pretty typical. One thing we did for the builders in Nelson was we took the house that had the worst results, and we sort of looked for the low-hanging fruit where we could make a really big difference in the carbon footprint with just a small number of changes. So we took the average concrete from that building and subbed out the results for a high SCM concrete, so something with a lot of slag or fly ash in it, and also like a Portland limestone cement. We changed the foam ICFs for wood chip ICFs. We changed the mineral wool wall insulation for cellulose. We changed the XPS continuous that building had for wood fiberboard on the outside. We changed, it had hardwood floors throughout. We changed half of those to linoleum, and we put cellulose in the roof instead of mineral wool, and we halved the carbon footprint of that building. So 6 relatively straightforward steps, nothing that is too difficult to achieve. In a lot of cases, not necessarily even any more expensive to achieve, and we can cut the carbon footprint of that building in half. We haven't addressed the design of the building or anything, just its these 6 material interventions. And then we decided to pick 6 where we could take it a little further. So we changed the EPS that it had under its slab for foam glass gravel. Again, we switched out the concrete. We changed the ICFs to a treated wood foundation, changed the walls to straw bale, changed the floors to a mix of linoleum and cork, and we put cellulose in the roof again. And that brought that 300 kilogram per square meter house down to just 55. So again, a handful of material swaps. The ones on the right may not be ones you're going to jump to immediately. They may not be things that you're considering, but all achievable, all things that people have done, and a pretty dramatic tenth of the carbon footprint of the original house. And then in that Nelson study, this house came to our attention after we had run the study, but the energy advisor who was helping us out there said, "Hey, I think I've got a pretty interesting little building." I ran it through the calculator just because I was curious, and it has 2 kilograms of CO2 per meter squared. So essentially a zero carbon house on the material side. And the biggest things that contributed to that were It had no concrete in the foundation. It's up on helical piers. That allowed it to have cellulose in the floor instead of any kind of foam in the slab. Cellulose wall insulation, wood cladding, and cellulose roof insulation. Not terribly radical as far as the building goes, but a radical change from sort of the average of that study in the 150 range down to basically a zero carbon building. And it was great, in that study to be able to talk to the builders and other folks in those two municipalities and say, like, this is actually going on, in your jurisdiction right now. You could be building this, everybody could be building this. You don't have to necessarily build it this way with these materials, but these kinds of results in terms of carbon footprint are achievable. It's not a pipe dream or anything. So I wanted to dive a little bit into the concrete because it does end up in most residential buildings being a pretty significant portion of the carbon footprint. Obviously, there's things you can do like not use it or reduce how much you're using it. So by sheer volume, you can make a difference. But also, asking your suppliers for just to know what the carbon footprint of your concrete is really helpful. And B, pushing them to start offering lower carbon mixes. So when I look at the concrete EPDs that are available across North America, I can see that there's a best achievable of only 136 kilograms of emissions per cubic meter of concrete. And I can see that about 20% of the EPDs are above 650 kilograms per cubic meter. That's a big split. Like, when you get to site and it's coming out of the spout, it just looks like concrete. There's no performance difference. This is for the same PSI. It's for the same like basic residential mix that anybody would use, but there's this giant gap. For our studies, we're using this Canadian average of 369 kilograms per cubic meter. But, by and large, we don't even know what people are using because most ready mix plants that are supplying residential buildings aren't producing EPDs. So, one of the things you can do is start asking your concrete supplier for, hey, can you make me an EPD for this mix that I'm getting? And if the numbers look terrible, like this one, 650, ask them to do better or take your business elsewhere if you can, because there's lots of things that they can do to bring that down. And just, the difference here is if we use the best number, the same wall, like 1,000 square feet of 8-inch wall could have, 2.5 tons of emissions or over 12 tons of emissions. So it's a 10-ton difference. It's still a concrete wall. It's just like if you looked at it, if you built a house on it, you would not know there's any difference, but the climate feels that kind of, 10 tons per house difference. So, everything we can do to make sure that we're bending that down is really great. For Nelson, we sort of did this little wall systems comparison. We just looked at some of the ones that were quite common across the houses we studied there. And you can see, basically we tried to normalize this so that all of these are achieving an R24 level of performance. And, you can get anything from, 9 tons of emissions from the worst case to 5 tons of storage in the best case, and kind of everything in between. So thinking about, how we pick those materials, what goes into the assembly is really important. I know there's a lot of people, I get like more email about this than anything else. Yeah, there's this new XPS formula coming out. It's a real game changer. It's kind of a game changer. It changes XPS from being like shockingly by far the worst insulation to being kind of just the worst by a little bit. So, it's not going to change the world, but it is a pretty significant improvement. And it makes it, about the same as doing mineral wool cavity and mineral wool board on the outside. So, glad that that's happening, but it's not sort of the silver bullet that it's sometimes being made out to be. This was interesting. I hadn't really thought about this because in my practice, I don't really build houses for cars, but a lot of people do. So 19 of the 35 homes in Nelson had garages, and they had 122 tons of emissions just from the materials that go into the garage. So basically 20% of the emissions from houses that had garages were attributable to the garage. So if you want to cut the carbon footprint of your building down, don't make a building for a car. You can knock a fifth off your total right there. Don't do anything else. Just don't make a house for a car. So I'll kind of go through this quickly. These are the takeaway points for the group in Nelson. I really want to make sure that people look at the first two here. Even though I'm saying that material emissions are a lot bigger than operating emissions, I am not at all suggesting that we give up on operational emissions and only think about materials. Like, I really think these two things need to go hand in hand. The kind of results where you actually get a real zero carbon building, it really has to be net zero on the operational side, and it needs to be zero on the materials side. You can't really just put all your attention in one place or the other. We really have to be doing these things hand in hand, and really, thinking about them holistically that way.